Hello everyone, today we're going to do quiz 5, KVL KCL circuit analysis for EE1305, fall 2019 at UTEP, Intro to E, Electrical and Computer Engineering. Right, so today, because of that, we're going to use KCL, KVL, and of course our good old friend Ohm's Law on the following circuit and solve for what we need. Right, what I always like to do, and I show in class, I like to draw Ohm's Law for a resistor based on our thing. So if we have resistor R, we have some voltage drop V, and that means current flows from the positive to the negative side of your voltage drop, right? So the first part is saying sketch the voltages, the schematic above, and that's using Ohm's Law, because what's the first thing we like to do when we solve this in class is label everything. So based on that, then I would do positive 1, this could be V1, and over here, positive, negative V3. It's a positive here, so I can put the negative here and a negative here. All right, so we've done that. Check. Okay. Now we can write our Kirchhoff's current law relationship for node A right here. We know with KCL, if it's going into a node, it's positive. If current's leaving a node, negative by our standard. So here we have I1 is going into the node, I2 is going into the node, so it's also positive. I3 is leaving, so it's negative, and that's going to be equal to 0. Okay. Now we can write our KVL relations for the circuit, right? So we have two loops here. We have loop A and loop B. And remember, we go clockwise direction. And if we hit a negative first, we write a negative sign, positive, positive. So we can do that. So for node A, right, we start in this corner because I'm a creature habit, and we go minus 9 volts plus, right, V1, which is I1 times 9 ohms, plus I1 times 9 ohms, right, plus 6 volts, all the way back is equal to 0. Right, and we can do the same thing for loop B. Right, I start in this corner, I get negative 6 volts, plus, and then it's I3 times 6 ohms, I3 times 6 ohms, and then we come all the way back around, and that's equal to 0. Right, and now we can solve this part here. So if we go to do that, let's first move things around. So we can rewrite this. We see that this one here becomes that I3 times 6 ohms is equal to 6 volts. If we just move this over, right, and that gives us that is equal, implies that I3 is equal to 6 volts divided by 6 ohms. This says that I3 is equal to 1 amp, right? It's pretty good. And now here we just have I1 in this equation, right? And this 3 is a little messy, sorry. Right, it's a 3. And here we have this, so if we move around, so if we add them, it's negative 3. So we can go, that this equation says that I1 times 9 ohms, right, minus 3 volts is equal to 0. Right, now we can rearrange. This is that, go up here first. This is that I1 times 9 ohms is equal to 3 volts, or I1 is equal to 3 volts divided by 9 ohms, which is equal to 1/3 amp. All right, so we get that I1 is equal to 1/3 amp here. Right. Okay, you see I got lots of room to work down here actually, so I'm kind of crowding the space. So we should, really, if we're using the space, move it down here. Right. So now we've just simplified these and solved, right? And of course, underline these here to make sure they stand out. So now we have I1 and I3. What we need is I2. We have this relationship right here. So we see that I1 plus I2 minus I3 is equal to 0. Right? So we can add I3 to both sides. So plus I3, and we get that I1 plus I2, those cancel, is equal to I3. Now you can subtract I1 here. We get that I2 is equal to I3 minus I1. Right, so now we've moved around, so we have I2 on one side are unknown. And we know this, so we get that I2 is equal to I3, which is 1 amp, minus I1, which is 1/3 amp. So that I2 is equal to 2/3 amps. So 2/3 amp. right? So 1/3, 2/3, and 1 amp, right? And again, what do? The first step, of course, always label everything using our Ohm's law for resistor, right? So you have a voltage drop. We go positives on the tail, minus on the tip. If we have any other negatives, we can do it. We can also label our KVL loops, and we have our node for KCL. Once we do that, we can write our KCL relationship, where if the current's going into the node, it's positive, if leaving, it's negative. Then we can write our KVL relationships going clockwise around the loop, right? And then we can simplify those. And finally, we can then use our KCL to solve for the last current, which we didn't know. So I hope this has been helpful. This has been Quiz 5. Comment, like below, subscribe to my channel. Thanks.